in the absence of not being able to do this activity in person, I'm going to walk you guys through it. I'm doing it here at home, and you can even do it along with me if you'd like. What you will need are 50 M&Ms randomly taken from a bag. You can take them from really any M&Ms bag you have, I guess. But your goal is you want to have 50 of them randomly selected. So you can even just shake up your bag and then count out 50 M&M. Dump out your M&Ms. Count up 50 of them. What I tell people is if you don't have enough, just dump a few more. If you have too many, pick 4 or 5 to eat. So what we're looking at here is this is our first experience with a Chi-Square goodness of fit test. Now, we've been doing hypothesis tests, and this is a bit of a different one. For a goodness of fit test, what you're really trying to find out is an advertised distribution of one variable true. And specifically, not just one variable, but we're looking at one categorical variable. So it's one specific category. So we're looking at, our data, and we're trying to, generalize it to a population. So we're looking at population, and we're looking at one category that has to do with that population. In this case, with the M&Ms, we're looking at specifically color. That is our categorical variable. Now, there are other tests for multiple categorical variables, but we're just focusing on the one. And if you're dealing with one categorical variable, trying to prove it's true, you got yourself a goodness of fit test. You will notice that I already dumped my 50 M&Ms out, and I counted them. If you want to do the same, you can. If you don't have M&Ms handy, you can just use the numbers that I have. I counted out 8 brown, 5 yellow, 3 orange, 7 green, 7 blue, and 20 red. I ended up getting a lot of red M&Ms and not that many orange. Now, M&Ms up here, you'll notice that they claim that 13% of M&Ms are brown, 14% are yellow, 20% are orange, 16% are green, 24% are blue, and 13% are red. Now, granted, we aren't always going to get that distribution from a random selection. There's always variability in sampling. What we're trying to see is it really likely that we're going to get a distribution that looks like this? If this is where our population really looks like? If our population is really, the 13% brown, 14% yellow, and so on, should we really be getting a sample that looks like what I got? That's what we're testing here. So we start out with a null and an alternate hypothesis. For my null, I wrote that the claimed distribution is correct. And for my alternate, I claim that the distribution is not correct. And it's always based on equal and not equal statements. You'll notice I wrote it out differently here using equal and not equal statements. What I did here was for my null, I had the proportion of brown is 13, proportion of yellow is 14, proportion of orange is 20, and so on, just like they advertised. And you'll notice I just used kind of little abbreviations here. P of G would be green, P of BL would be blue, P of R would be red. For my alternate here, I literally just copied and pasted what I had here, and then I put don't equal signs. I crossed out the equal sign, put don't. And I stuck ors in between everything. Why? Because really it only takes one color to be off to set a few things off. Hey, let's look at what I had here. I had a lot of reds and not too many oranges. So that would really throw off these two proportions based on what I did here. I got way different proportions based on these two. Now, all it takes is for those two to be off to really disprove what M&M said. Maybe they threw a bunch more red in than they said, and maybe they didn't use as many orange as they said. So it doesn't necessarily have to be that all the proportions are incorrect. It's usually just going to be 2 of them, maybe 3 or 4. You never know. So here's what I did. I calculated if M&M's is correct with their distribution, what would I expect to see from my 50 M&M's? In order to do that, to find these what we call the expected counts, I took that proportion that they advertised, the 13%, and I multiplied it by the 50. Because, I have 50 M&Ms. If 13% of 50 M&Ms are supposed to be brown, it tells me I'd be expecting to see 6.5 browns. Now, of course, we know that M&Ms doesn't typically give you half M&Ms, at least on purpose. But you want to retain your decimals here. You're going to see down the road, the more you do this, that rounding the whole numbers isn't to your benefit. Of course, your expected values aren't always going to be perfect. That's okay. Because you're not always going to get your expected values. You're just hoping that what you get is really not that far off from what you expect. I mean, if you got 7 instead of 6.5, okay, then maybe M&M's isn't wrong. Maybe if you got 5 instead of 6.5. Okay, maybe M&M's really isn't wrong because, again, you expect variability in sampling. Notice I did that for every single color. 14%, which I got up here for the yellow, 14%. Multiply that by 50, got 7. I'd expect 7 yellow. 20% are supposed to be orange, so I multiplied that by 50, got 10. 16% are supposed to be green. Out of 50, I'd expect 8. 24% are supposed to be blue, so out of 50 M&Ms, I'd expect 12. And then 13% are supposed to be red, so out of 50, I'd expect 6.5. Now you'll notice you have a table down below here to calculate some values. So you start out with the brown. I had 8 brown M&Ms. That's my observed. What I expected 6.5 based on my calculations. I subtracted those two values and I got positive 1.5. I then squared my values. Now I get this question, why do you square your values? The reason is because you're trying to see how close you are to what they advertised. If you have some that are less and some that are more, you'll notice that if you just add those values, it's going to cancel out. It's not going to necessarily reflect that you're off from your proportions. Like as an example, say I had 10 more red M&Ms than I expected and 10 less orange than I expected. If I took those differences and, positive 10, negative 10, they cancel out. So then you'd be like, oh, okay, well, M&Ms it really isn't wrong. When in actuality they are, because they give me a lot more reds and not that many oranges. So that's why you square your values. So that way you can make them positive and it actually reflects that difference. So again, I did 8 minus 6.5, got 1.5, squared it and got 2.5. I did that for all of them. I observed 5 yellow M&Ms. I expected 7 of them. That gave me a difference of negative 2, which I squared and I got positive 4. For orange, I observed 3. I only got 3 when I was expecting 10. I had a difference of negative 7. When I square that, I get 49. For greens, it was really close. I got 7. I expected 8. So there's only a real difference of negative 1. Squared that, I get positive 1. For blues, it was a little bit off. I observed 7. I expected 12. Negative 5. Squared that, got 25. Now here for the red is where I got a big number. I observed 20 red M&Ms and I only expected 6.5. That gave me 13.5 when I subtracted my observed and expected. Now, if I took all these values just right here and I added them up, just my negatives and positives, you're going to notice that you get a value pretty close to 0, which really gives you the impression that, okay, well, M&M's really isn't that far off from what they advertise. In actuality, I did get quite a big difference here between my oranges and my reds, so I want that to be reflected, which is why I squared these values. Next thing you do, you take that value of observed minus expected squared, and then you divide it by what you expect. You'll notice I did that in each case here. I took observed minus expected, 2.25, divide that by 6.5. I did 4, my observed minus expected squared, divide that by 7, what I expected. Did the same thing here. That 49 is observed minus expected squared, divide that by what I expected, 10. I did that all the way down here. And, I calculated my values, and then I added them up. And this is what's called our test statistic, our Chi-Square statistic. That's how you would get a Chi-Square statistic by hand. A lot of times your calculator will do it out for you. It's a pretty nifty function, and I'll walk you through it, but it is good to know where these numbers are coming from. Because you'll notice you get some pretty high chi-square values for the ones you probably expected. For the red right here, you have a really high one. For the orange, you have a pretty high one too, 4.9. That's a pretty high chi-square statistic. Whereas for these colors here of like yellow and green that really weren't far off from what we expected, we ended up with some pretty low chi-square values here, like, less than 1. So that's what you'd expect to see. If you're getting something that's really far off from what you expect, you'd get a really high chi-square statistic. If it's not that far off, then you're not going to get a very high one. So that's how you arrive at your chi-square statistic. In the next video, I'm going to walk you through how you can use that chi-square statistic to find a p-value, to find the probability of actually getting this distribution if what M&M says is true. I'll actually walk you through the conditions as well as